Welcome to Bazai, where builders ship agents faster. If training agents still feels like wrangling GPUs, YAML, and brittle scripts, this walkthrough shows a faster path. An open-source pipeline that trains a large language model to play 2048 with agent rollouts, reward shaping, and automatic deployment without managing infrastructure. By the end, an agent powered by Qwen 314b with a lightweight LoRa adapts to the game, logs everything to experiment tracking, and hot-loads the latest weights behind a standard chat interface. What you'll learn. Here's the plan. First, why 2048 is ideal for Agent RL. Then the mental model, a trainable model, a backend that runs training and inference, and a loop that turns episodes into trajectories with rewards. Next, the environment spec for 2048, the rollout that drives moves, and the reward shaping that teaches winning. We'll close with observability, instant deployment, and how to reuse this blueprint for practical agents like email research and data routing. News segment, Serverless RL launch. Quick news, October 14th, 2025, Serverless RL launched. It lets you post-train LLMs for multi-turn agentic tasks using reinforcement learning to improve reliability and speed and reduce costs without provisioning or managing infrastructure. There's a collab you can run today to see the full loop end-to-end. You keep control over examples, environments, rewards, and hyperparameters while training runs for you on CoreWeave's distributed clusters. It sits within WNB training alongside ART, a flexible RL fine-tuning framework, and Ruler, a universal verifier, plus a fully managed serverless backend to run RL loops with zero GPU setup. Why 2048 for agent training? 2048 compresses long-horizon decision-making into 4 actions: left, right, up, down. It's deterministic in merges but stochastic in spawns, which is perfect for multi-turn rollouts and testing whether a policy can learn stable patterns. To iterate fast, set the win threshold lower, like 64 instead of 2048, so the agent sees useful signals sooner and you observe learning within minutes, not hours. Framework mental model. Think in 3 layers. First, define a trainable model with a human-readable name, a stable project for grouping runs, and a base model like Qwen 314b Instruct or your local SFT LoRa. Second, choose a backend. Serverless for auto-scaling GPUs, remote ephemeral for controlled runs, or local for debugging. Third, the learning loop. Define scenarios, run rollouts to collect messages, choices, and rewards, update LoRa, and hot-load the latest weights for inference automatically. Backends at a glance. Serverless, zero infrastructure to manage, auto-scaling GPUs for RL, and automatic hot swap of the newest adapter. Remote ephemeral. Spin up a dedicated machine or cluster for heavier experiments or scheduled runs. Local. Iterate fast on your box, then scale later without changing client code. Show the PPT here, a diagram linking trainable model backend inference with arrows showing gather, train, deploy, and a note. Inference always routes to latest LoRa. Client initialization flow. Initialize the trainable model with name, project, base_model, then register the backend. That single registration wires training and inference to the same endpoint. Every time the loop completes a step, the newest LoRa is loaded, and your OpenAI-style client keeps working unchanged. Optional. If you have an SFT LoRa directory already, point base_model to it to warm start RL. Warm start rationale. Warm starting stabilizes early training and reduces GPU steps, especially on smaller models that might otherwise struggle to find non-zero rewards at the outset. The adapter becomes your initial checkpoint. RL updates refine it from there. The 2048 environment spec. Environment design is simple and robust. State, a 4x4 grid of integers or empty cells. Initialization, seed 2 cells with 2s or 4s, usually 2s 90% of the time. Moves, condense rows or columns, merge adjacent equals once per move, fill gaps, then spawn a new tile in a random empty cell. Rendering, output a clean, monospaced grid as text for the model. Termination, win when a tile reaches the target or when the board is full. Metrics, max tile, total board value, move count, used for reward and analysis. Action schema and prompting. Constrain the model's output to a strict schema, like an XML snippet, move left/move. The user message is just the board text. The rollout parses the XML, applies the move, and continues. If the output is malformed or the direction is invalid, end the episode with a penalty. This keeps rollouts deterministic and teaches schema discipline alongside strategy. Rollouts and trajectories. Each rollout plays a full game and returns a trajectory, a list of messages and choices across turns, plus metrics and a reward. The loop appends the system prompt, shows the board, gets the XML move, applies it, and repeats until termination. At the end, compute metrics, max tile board sum, moves, and assign a reward. Invalid outputs end early with a negative reward to reinforce correct formatting. Reward shaping that teaches winning. Prioritize wins with a strong fixed reward. Otherwise, combine two signals. A log-scaled max tile score that strongly nudges toward higher tiles. A log-scaled total board value that encourages consolidation instead of chaotic merges. Weight the max tile higher so the policy seeks the real objective, while the board value provides a smoother gradient to improve mid-game play. Training loop and parallelism. Training runs in steps. For each step, launch many rollouts in parallel, multiple games at once. Gather trajectories grouped by scenario, prune old or weak checkpoints, and run a LoRa update. While weights update, inference briefly pauses, then the newest adapter hot loads. Immediately, client calls hit the updated model. Show the PPT here with a counter stepping 1N and a caption, gather train hot swap serve. Observability and evaluation. Track max tile distribution, mean board value, win rates, and episode lengths across steps. Drill into any trajectory to inspect the exact board sequence and the XML moves taken. This is where you'll spot schema mistakes, repetitive loops, or plateaus. Tweak prompts, tighten penalties for bad output, or adjust reward weights when signals are too sparse. Live demo and deployment. Once a few steps complete, query the current step, form the deployed model name with that step, and run a fresh game. Every 10 moves, print the board, the agent's XML, and the updated board. As learning progresses, you'll see consistent patterns, anchoring high tiles, avoiding fragmentation, and steering merges toward structure, ultimately hitting the simplified win condition reliably. From 2048 to real agents. Swap the board for your domain context, emails, documents, or tool outputs. Replace the action schema with JSON or XML tool calls. The rollout orchestrates retrieval, planning, tool execution, and checks until a terminal signal. Rewards map to business outcomes, accuracy, recall at K, latency, or human feedback. Because the backend auto-deploys the newest adapter and your client surface stays the same, the path from experiment to production is a configuration choice, not a re-architecture. That's the blueprint. Define your environment and strict action schema. Write a rollout that returns trajectories with rewards, run the step loop, and let the backend auto-scale training while serving the latest adapter. Welcome to Bazai. Subscribe for weekly deep dives on agents, RL, and open source tooling, and drop questions below for the next build.